Hi everyone, I'm Marius, and today I'm going to be presenting our work on boosting CNN inference acceleration performance with AI-optimized FPGAs. Starting off with a bit of background info first, convolutional neural networks are a type of network used for computer vision tasks, typically things like self-driving cars or facial recognition, but some more niche applications published recently include galaxy classification or automated fruit farming. These require billions of multiply accumulates in the forms of convolutions, shown on the right here in the animation. So in a convolution, we take a 3D filter or set of weights and multiply it against a 3D input set of activations, activations being the result from the previous layer. In this case, we have red, green, and blue color channels. We accumulate all the results of this multiplication to form one output, and we repeat this multiplication over the entire input width and input height to form one output channel, and then we repeat this entire process over multiple different filters to form multiple output channels. One special type of convolution, which we'll discuss in this work, is the depthwise convolution. So for the depthwise convolution, we essentially don't accumulate across the depth of the filter, and instead the number of input channels is always equal to the number of output channels. Since these convolutions are parallel and friendly flow precision, we can use FPGAs for custom hardware acceleration. They're rapidly configurable and easy to tailor for specific networks, and this means they're much faster to deploy than something like an ASIC. They're power efficient compared to GPUs, and they're also customizable, meaning we can optimize them for lower precision data types. HPIPE, which we build upon in this work, stands for Heterogeneous Pipeline Engine, and it's essentially an in-house Python compiler that generates custom Verilog hardware for every layer in your neural network to accelerate the network in hardware. It's layer pipelined, meaning we don't have to wait for the previous layer to finish essentially computing before we can start the computation in the next layer, and it also has a deep configurable pipeline resulting in a high Fmax. This generated Verilog hardware is compiled in Quartus and then deployed on the Stratix 10 line of FPGAs. We support sparsity, meaning we don't store any weights that are close to or equal to 0, and we don't do these computations either, so we can achieve higher performance through this. We store all parameters on chip, and HPIPE outperformed all prior work at the time it was originally published, so it was 9 times faster than Microsoft Brainwave and 3.5 times faster than the NVIDIA V100 AI-optimized GPU. So the original HPIPE design used standard DSPs found in the Stratix 10 line of FPGAs. So these DSPs feature just two 18-bit multipliers and an accumulate. The Stratix 10-NX line of FPGAs, however, features up to 30 8-bit multipliers instead. And these tensor blocks take up the same amount of area as the regular DSPs with their 30 multipliers. Creating these smaller multipliers is cheap relative to the fact that the extra inputs and outputs to the programmable routing are expensive. And so we have data restrictions on the multiplier inputs and outputs. So the question becomes, how can we reorganize computations to fully exploit this? Well, there's 3 different tensor block modes which we take advantage of in our work. The first is scalar mode. So in scalar mode, we use the least amount of multipliers in the tensor block. We have the least amount of restrictions as well. So we have 3 completely independent multipliers here and 3 independent outputs here. But again, we're only using 10% of the multipliers inside the tensor block. Vector mode has more input and output restrictions, but we double the multipliers compared to scalar mode. So we have 6 multipliers, but we have restrictions in the sense that we must accumulate the results of these multipliers, and then we only produce one output. Tensor mode uses all 30 multipliers, but also has the most input and output restrictions. So we operate in vectors of 10 values. Each value is 8-bit. And for these vectors, we must preload 3 of the vectors into a set of ping-pong registers before we can use them for computations, whereas the other set of vectors is then broadcast in afterwards. So we preload 3 vectors and then use 1 vector to multiply against all 3 preloaded vectors. And so in the dot product engine, we perform our 10 multiplications, accumulate the result, and produce 3 outputs. So now, last bit of background info is the baseline HPIPE convolution engine. So I have an example here on the left. So we have our input activations, the results from the previous layer, 10 input channels. We're multiplying them against 3 different filters, red, green, and blue in this case. And we're producing an output with 3 output channels. So there's three different types of parallelism you could take advantage of here in HPIPE. The first is called input channel parallelism, and this can be tailored in our compiler. In this case, the maximum it can be set to is 10. So this is the number of input channels we are multiplying against the filters in the same cycle. And so to achieve the maximum parallelism of 10, we instantiate a chain of 5 DSP blocks here, so 10 multipliers total. And these are chained in an FPGA column. And so we're multiplying our inputs and then cascading the results down the chain and accumulating them. Second type of parallelism, this is built-in parallelism, so it's always maximized. It can't be tuned by our compiler. And this is output width parallelism. So this is how many output values across the width are we computing in the same cycle. In this case, it is set to 10. So what this corresponds to is, so in a convolution engine, which is one of these colored blocks here, we have a certain amount of dot product engines. These dot product engines are the DSP chain we just discussed. And so in this case, we would have 10 of these dot product engines computing results in parallel. The last type of parallelism is output channel parallelism. So this is how many of these filters are we multiplying against the input activations in parallel. And to take advantage of this one, we essentially duplicate the convolution engine. So over here, we have the same convolution engine duplicated 3 times, one for each filter. The weight buffer in each one will store a different filter, but we're sending identical activations to each one. These activations are stored in the activation buffer, and then they're steered into the dot product engine. Same with the weights shown here. So next, jumping into our implementation. So we have 2 different implementations on the Stratix 10NX. We have a sparse implementation and a dense one. We'll start with the sparse one first. So for the sparse implementation, which we maintain the weight sparsity discussed earlier, we use 2 different modes. The first is vector mode. Vector mode, recall, can perform 6 8-bit multiplications and an accumulate. And this is because we're limited by the number of inputs and outputs in a DSP block, so we can't use all 30 multipliers if we want this much flexibility, which we do need for sparsity. So mapping HPIPE to vector mode increases our computational density at 3x at the cost of lower precision. So we're using 8-bit instead of 18-bit. We still support sparsity as the inputs are completely independent, and we have some additional accumulation restrictions which result in extra soft logic. So zooming in onto our example from earlier, this chain of 5 DSP blocks shown here will now turn into just 2 tensor blocks where 2 of the multipliers are unused. And again, each tensor block takes up the same amount of area on chip as a DSP block, and so we get some area savings here, which can be used to achieve higher parallelism settings overall. The second mode we use is scalar mode. So scalar mode can perform 3 independent 8-bit multiplications, uses the fewest amount of multipliers, but the fewest restrictions on inputs and outputs. And so this comes back to the special type of convolution we discussed earlier, which is the depthwise convolution shown here. So recall a depthwise convolution applies a single filter to each input channel so that the number of input channels is the same as the number of output channels. And what this essentially means is that since we're not accumulating across the input channels anymore, we have one less degree of parallelism to exploit, that being input channel parallelism, which is always set to 1. And so if we were to use vector mode, we'd only use 1 out of 6 multipliers. So we can use scalar mode to more effectively pack these convolutions on the NX. So going back to our example from earlier, if we were implementing a depthwise convolution, we'd have 3 dot product engines shown here, where most of the multipliers are completely unused. Instead of using vector mode, we can use scalar mode, where all 3 of these are combined into 1 tensor block, producing 3 independent outputs. Next, I'll cover our dense convolution engine. So our dense convolution engine doesn't take advantage of sparsity, but it's able to use tensor mode. So tensor mode has 30 total int8 multipliers, but we operate in vectors of size 10. And this is also why we can't take advantage of regular sparsity. Our sparsity would need to be in blocks of size 10. And what we found in our work was that this type of sparsity was hard to exploit. You would need a special training process, which was sort of outside the scope of this work. And so to take advantage of tensor mode, half your data has to be preloaded into a set of ping pong registers. And so while you're preloading one set of registers, for example, you can use the other set of registers to perform your computation to hide that loading latency. And then you essentially multiply those preloaded values against one vector broadcast in here. There's 3 different preloading methods which we could take advantage of. The first is data input mode. So for data input mode, we're using the entire or almost the entire data input bus to load our values over 3 cycles. So it's 10 values over 3 different cycles as we have 3 different registers here. But since we're using this entire bus to preload value, we can't essentially hide the loading latency with computations. The second type of preloading method is side input mode. So for side input mode, we load 2 values at a time over 15 cycles, and that essentially leaves 10 inputs here available to use for computations. And so we have a longer loading latency, but we can hide that latency with computations if we can reuse enough data. The last type of preloading method is cascade mode. So in cascade mode, we need an extra type of tensor block at the top of the chain. And this is essentially just a tensor block configured to use data input mode, which won't be used for computations. But the rest of the tensor blocks in the chain will use cascade mode. And so for cascade mode, we load values 10 at a time over 3 cycles. So it'll take 3 cycles times the number of tensor blocks in your chain. And you're sending these down a dedicated cascade wire down the tensor block chain. And so you can hide the loading latency here as well. So the question becomes, what is the best preloading method, and should we preload waits or activations? To determine this, we did a performance analysis before implementing our design. And what we found was that for preloading waits, shown in red here, we got a lot of stalls. So for preloading waits, to hide the loading latency, we need layers with larger output widths. But for most networks, as we go deeper and deeper, the output width decreases. For preloading activations, shown in green here, we found no stalls in the mobile nets, and this was because for preloading activations, the latency can be hidden with larger number of output channels, which does happen as we go deeper and deeper in most networks. Between cascade preloading and side channel preloading, we didn't see any major performance differences, and so we went with cascade preloading for timing reasons, as that means we only need one big memory at the top of each chain rather than multiple smaller memories beside each tensor block. So this is what our implemented tensor mode convolution engine looks like. I'm just going to provide a high-level overview here of the data flow. So we have our input activations. These are the results from the previous layer. They get sent to the tensor activation buffer. Once we have enough values buffered here to start the preloading process, we send the values down this dotted wire. So following this dotted wire into the dot product engine, you'll see it goes into the top tensor block in the chain. This one's not used for computations. And we cascaded the values down the tensor block chain as shown here. Once we've preloaded all the values, our wait memories can start sending in values into the dot product engine. These are sent to the second and third tensor block in this example. And here we compute the dot products in the dot product engine shown here, accumulate the results, send them down the chain, and accumulate them there as well. These get sent to the tensor output buffer, where we store these partial results until we have our final output, which we can send to the next layer. Next, going into some results. So first, we're gonna look at cycle count simulation results. So this is just to sort of compare the raw performance of each mode while ignoring any frequency concerns. Vector mode comes close to the peak performance improvements of 3x, so that's the red bar here, compared to the baseline blue bars shown here. So recall that vector mode supports sparsity but has fewer multipliers. Tensor mode, shown in the green bar here, falls short of its peak performance improvement of 15x based on the number of extra multipliers we have compared to the DSP implementation, but still provides good speedups. And this limitation is due to a couple things, the two main ones being unused tensor blocks at the top of each chain as we use those for preloading, and then depth-wise convolutions in all cases in this graph have to use scalar mode, which means they're only using 3 out of 30 multipliers. FPGA results. So I'm just going to highlight 2 results here. More detailed results can be found in the paper. Sorry, 1 result here for Mobilenet-v1. And so what we found was that the larger bus sizes result in a lower frequency. Since we're operating in these larger vector sizes, we take a drop of about 100 megahertz compared to a DSP-based design. But the higher parallelism still results in higher performance overall. Next, a comparison to prior work. So for the Stratix 10NX, we don't know of any other CNN accelerators at the time of writing the paper, at least. However, we do know of a NPU described in reference 7, which accelerates operands on the Stratix 10NX and achieves 3.5 times higher performance compared to their baseline design. And this is compared to our 7.1 times performance improvements when we look at our baseline design. Other FPGA accelerators, we outperform them by at least 4.7x, and you can see the paper for a more detailed comparison. The Xilinx Versal is another AI-optimized FPGA. This is a 7-nanometer AI-optimized FPGA with AI engines that are sort of separate from the FPGA fabric. In reference 8, the authors get almost 3,500 images per second on Mobilenet-v1 SSD. This is a larger network, so when we scale their results to match the smaller version of Mobilenet-v1 we used, we still achieve 4.0 times higher throughput than their implementation. And compared to GPUs, so we looked at the NVIDIA V100 AI-optimized GPU as it has the most similar die size, although much higher power consumption. And we found that we outperformed it by 6.2 to 17x at a batch size of 1. And we even outperformed it at a batch size of 128 by 1.3x. And in the past, this is typically where GPUs have always outperformed FPGAs at these higher batch sizes. So in conclusion, tensor blocks can be exploited well for convolutions, but we need to use multiple modes. So scalar mode can be used to pack 3 depthwise convolutions together. Vector mode is well suited for sparsity and achieves speedups of up to 3x. Tensor mode is not well suited for sparsity, but achieves much higher speedups than vector mode just due to the extra multipliers. So it achieves speedups of 8.3x in total. FPGA frequencies are lower than standard DSP blocks, but speedups of up to 7.1x are still achieved. And so what we found was that we outperformed all prior FPGA CNN accelerators by at least 4x, and even the AI-optimized NVIDIA V100 GPU by 17x. And so we discussed some tensor block architecture recommendations for further gains in the paper, as well as some future work there. And this concludes our presentation. Thank you for watching.